We are on 12.3, continuing. Let's look at this example, kind of a short one. So let's try this example. Find the angle between the vectors. So you're given the vectors u as 1, -1, 2, w, -1, 0, 1, and apply the theorem above, right? So we want to apply this one. So essentially, to find the angle, we're going to use this formula, not so much this one. So we can convert back and forth. You want to change it into a dot product, then you know it. You go from here to here. If you want to find the angle, it's going to be cosine inverse arc cosine to solve it. And this one, not an exact form, so you just leave it as arc cosine. Okay, so give that a try. This one I'm not working out. I'll just unhighlight everything. Okay, so first thing we'll do is you write, actually I just did that. So theta is arc cosine of u dot w over magnitude of u, magnitude of w. So you got to calculate each of the magnitudes and do their dot product. Okay, so I did this separately here, right? See that? These are kind of separate. So u dot, and I wrote v, that's actually w. So that's w is 1. How convenient. And then you do their magnitudes separately. Magnitude u, magnitude w is √6 and √2. Okay, and then you substitute in, and that's what you get. So, so you get, you can simplify it. There's no need to rationalize or anything like that. So it's arc cosine of 1 over 2 √3. And exact form is what I want. I really don't care about approximations in most cases in this class. Okay, so that was just a quick example of application of that. Not really the type of question we'll be asking directly. That's pretty straightforward stuff. So let's continue. This is on projections. This is applying some of those properties above with a specific type of question. So this is on projections. So suppose you had this picture. You have, kind of a surface. Okay, so we'll just call that, like it's like an x-axis, but it's just a surface. And then suppose you have a point in space or in a plane, doesn't really matter. Actually, I want to shorten this just a little bit because I want to make that an actual vector. So you have something like this. Okay, so you have a well, actually, you know what? Keep going. You'll see what I mean in a second. So you have a point in space. We're going to call that point R. And we want to find basically the distance, the perpendicular distance from that line. So this is basically point to a line distance, although this is the definition of a projection. So you have a point P here, and where this drops down, we'll call that S, and we'll define this vector basically here to my vector A. So we're going to create this vector PR, and we'll call that vector B. So what we're looking for is a projection of B onto A. We're looking for this vector. And that'll be considered the projection of B onto A. Okay, so that's the concept of projection. So let's take a look at this question. So we have vector PR or B. We'll just call it B. And we have vector PS. Okay, and so what we'll do, so we have those two vectors, and we're going to define it. We have an angle between those two vectors we're going to define. So we're going to theta is the angle between them. So we'll say we're going to let theta is the angle between B and PS. So we'll put that angle in there as such. All right, so then applying the formula above, we have that cosine. What's the cosine theta of that? Back up. What is the cosine of theta equal to? Well, that is going to be magnitude of PS over magnitude B. Oh, I kind of jumped ahead of myself there. If we look at the cosine of theta, it is, what's cosine theta? Cosine theta is adjacent, which is a magnitude, over hypotenuse, which is the B. So this is so actually I meant to write adjacent over hypotenuse and then show you that next thing later. Oh, see, and I'm not even gonna edit it. I'm just gonna keep going. Okay, so cosine theta is adjacent over hypotenuse. That's where I wanted to start. I think I usually do that on the board or something, is why I didn't even have it on there. But that's what I wanted to start with a right angle, because that's a right angle here. All right, so with magnitudes and vectors, you say cosine theta is magnitude of PS over magnitude of B. Okay, now you're with me. All right, so that's equivalent to, or if and only if. Now we can substitute now for cosine theta. So cosine theta is A dot B over magnitude A, magnitude B. Okay, and then it's going to equal, so that's just the left-hand side of, that's just cosine, right? That's just the definition. We're using this vector here, and you basically, it's like you're given a line, and then you're just going to know that vector. You'll be able to create that vector. We'll get to that much later, but a couple sections up. So it's equal to magnitude of PS over magnitude B. So do you see now we can eliminate magnitude B in both sides here. And so that's then equivalent to all non-zero vectors and stuff. Didn't make that rigorous assumption, but all non-zero vectors. So magnitude PS is equal to A dot B over magnitude A. Okay, and that is defined to be the component of B in the direction of A, right? You're projecting this down to A. So that's a scalar. Okay, so it's fixed. Okay, so this is some scalar in R. So then PS, basically you need to scale A. So what you do is you take A, you make it a unit vector. So how do you make it a unit vector? We divide by its magnitude, and then you multiply by the component. Okay, so that's the technique. Then you get the definition of the projection. So PS is equal to the component, so it's basically component of B onto A, that's how you say it, times the vector, the unit vector in the direction of A. First you got to unitize it, and then you multiply by the component. And then we simplify that, substitute in what we have defined to be the component right here, and then you reduce. So the substitution would be A dot B over magnitude A times A over magnitude A. So a little rewriting, and then you'll have the scalar you multiply A by to get PS. That's exactly what we're looking for. So you just rewrite this thing as essentially you put all this together. So you just take all this and put that together, and then you have A on the outside, which would be like the given vector. So it's the projection of PR onto A is what you're looking at. So it's A dot B over magnitude of A squared. That's your coefficient, and then it's times A. So that is considered to be the projection of B, the vector B, onto A. So that's how you say it. So it's A dot B over magnitude A squared times A. And then we'll look at an example. So, I mean, it's not like a formula like you're not going to just apply the formula. It's really this technique of how to manipulate the vectors into dot products and vector operations. I'll just call them vector operations. Is really what I'm getting at here. I mean, there'll be some homework that's just evaluate, but in like this next example, but really try to see how I'm putting all this together. The difficulty is, I think at first when you're doing this class, is all the notation. There's all these subscripts and magnitudes and vectors and, oops, I thought that was my highlighter, that you're doing. Okay, so let's do an example of this next one. So let U equal 2, -3, and V equal 1, 4. And then just basically do that. So find the projection U onto V. So to do that, we basically apply that formula. And it has to be the right order. So what we're looking at, so we got to do a couple things. We got to do the dot product. We got to do the magnitudes. So let's just do that. So u dot v is equal to -10. Magnitude, we're going to need magnitude of v, right? Because that's the order you need it. That's what's given, or the component. It's the square root of 1 squared plus 4 squared, which is the square root of 17. Okay. And then, if we write that in that form, the projection of u onto v. So you just got to picture u is your b and v is your a, and then that's what you get. And then rewrite that formula again. So it's u dot v over magnitude of v squared times v. Okay, so it's not obvious like how you get this. It's that whole derivation we did above is why you get things to reduce and simplify. But now you're finding this without trig. There's no trig going on. You're just doing vector operations. That's the real key to this question. Is basically we're getting away from the trig concepts and angles, essentially because when you talk about angle between an n-dimensional vector, it just doesn't make sense. Okay, so that's the projection. Okay, next is the concept of work. Okay, so we'll talk about work. All right, so work is a quantity defined to be what? If you know it, write it down. Say it out loud to yourself. Work is force times distance. So basically, it's a force, magnitude of the force times the distance. So for vectors, let me show you a picture here. So draw this picture just to kind of give you an idea. So you have something like this. And then let's just copy that. How about that? Oops. No, it's not coming up. Oh, there we go. Okay, so you want to move that object. Or push it. So if the force is in the same direction that you want to move it, like that, that's your F or your force vector. And then let's just pick this point P, and then we'll go to this point Q. Then that's your vector PQ. You can create that vector. And then work, in this case, is really simple. It's just magnitude of the force times magnitude of the vector PQ, the distance. That's the distance, right? Okay, so that's all nice, well and good, but that's not what we're going to do, right? We're going to have a force that's acting on it with an angle. So I'm going to use my technology and recopy that, and then paste it. And then do a different picture. Let's do a little farther down. That looks good. Okay. I know it's totally cheating, huh? Okay, so we're not going to quite do it like that. We're going to have a projection, basically, of this. So suppose the force now is like that. So this is F. And then that's the angle of the direction that you're pushing it. It's still PQ right there. So now work is defined to be the magnitude of the projection of F onto PQ times the magnitude of PQ. And I'm not going to get into the simplification on this one because we just did bunch of stuff above. That will reduce down to, with wonderful mathematics, simple algebra, or simplification of mathematics, into a dot product. Ends up just being F dot PQ. So that's really what I want you to focus on in the homework is a type of question just gives you the dot product. So let's look at an example where you would apply that question. So a force is given by a vector, and so this vector is just F equal to 3i plus 4j plus 5k, and moves a particle from a point, so from P, we'll call the point, what I have here, 2, 1, 0, to Q, which is 4, 6, 2, find the work done. So find the work done. So force vector acting on it. And so we know then that work is going to be just, we don't have to do magnitude, it's just F dot PQ, because when you do that dot product, right, that ends up being a scalar. So our force vector is given, so that's going to be our force vector. I'll write it in this component form, 3, 4, 5 dot PQ. So how do I find PQ? Well, I need to do that in component form, right? So I got to create PQ, terminal minus initial. So it's going to be 4 minus 2. Is it PQ? Yeah, P to Q. So terminal is Q. And then 6 minus 1. And then 2 minus 0. So calculate your PQ, and you get 2, 5, 2. And then you just do that dot product. So it's equal to force vector 3, 4, 5 dot 2, 5, 2. And then you do that calculation, you get 36. And I didn't give you units or anything. Units are in usually Newton meters, which is a joule. And again, just figure out what the units are for the question, and then do your best to write it down. Okay. So there's other homework questions, give them a shot, but I want you to focus on the questions where you end up having to do a dot product to get the force vector. To get work, sorry. All right, next concept, last concept we're going to do in 12.3. This is called the Cauchy-Schwarz inequality. This is an important inequality we look at, and it will help us prove the triangle inequality for vectors. So this will take a page, so let's just go down here. So let's just continue down and do this here. So this is what's called the Cauchy, C-A-U-C-H-Y, Schwarz inequality. All right, so it looks like this. So let A and B be vectors. In R2 or R3, it doesn't really matter. Then the absolute value, because it's a scalar of a dot product, so absolute value of A dot B is less than or equal to magnitude A, magnitude B. All right, so this one's pretty, now that we have the formula above that we spent that time proving, this is relatively easy to show, this inequality. All right, so let's look at the proof of that. So 1, if either, this is the trivial cases we call it, if either A or B is the 0 vector, that's it, we're done. Nothing to prove, right? Because you'll get 0 here is equal to 0. So that's it. So let's get that case out of the way. And then let's look at the second case. So 2, assume A and B are non-zero vector, and let theta be the angle between them. Okay, just like before. But you want to say it. These are the sort of stuff, we're getting more rigorous a bit in our mathematics. These are little details you need to be able to say and communicate with your reader. In most cases, it's me, but still. Right? So then, what we get is this. Let's start on the left-hand side. We're going to start here, and we'll work to the right-hand side. So if we say absolute value of A dot B, we can then apply the formula we just did. That is absolute value of magnitude A, magnitude B, cosine theta. Okay, and then that's equal to, well, magnitudes are going to be positive, so we can drop the absolute value for the magnitude. So it's just magnitude A, magnitude B. So then it's absolute value of cosine theta. Right? Where, oh no, I already said that. Okay. And so I don't need to say what theta, I already defined theta, so I already did that above. All right, so then what we're investigating now is really just that. What do you know about the range of cosine? Think about it. So since 0 is less than or equal to absolute value of cosine theta, which is less than or equal to 1, we have that A dot B is less than or equal to absolute value of A dot B. Okay, that's just because it can be negative as well. And see what we have basically. So you have this, and then this quantity here is always going to be smaller. So that we get that is less than or equal to magnitude A, magnitude B. Okay, so think about how that works. Like, why does that inequality work if the magnitude of cosine is smaller? Okay. All right, so then that lets us prove much more easily the triangle inequality. So let's take a look at the triangle inequality. again, the reason we're doing this is we can apply all these concepts that we just did. Just to show you again here, basically, if you multiply this by a fraction, like a half, it's always going to be smaller. So these are equalities, right here, but this basically is a fraction. So if you take it away, then this has to be larger. I'm not sure I explained that like that, but that's what it means. All right, so triangle inequality for vectors basically says this. So magnitude of A plus B is less than or equal to magnitude A plus magnitude B. So sorry, sometimes when I hit that thing down there on the very bottom, it does that. So you have vectors A and B, so I'm going to draw the vectors over here. So let's suppose that is vector A, and then this is vector B. Let's do it like this. And this vector is A plus B. It's kind of the form. So the magnitude of, so this length is less than or equal to the sum of those lengths. That's what it's saying. And it's this form with vectors. So it's an inequality we often see and use a lot. So I always want to have to prove this sucker. So let's take a look at the proof. What you do on this proof is you start off with this square. So you start off with the square of the magnitude of A plus B, and then rewrite that into a dot product, just like our. And then it should. And these are the properties we just talked about. That's A plus B dot A plus B, right? Because it's the dot product. It's this one. Magnitude of V squared is V dot V. Okay, and then multiply that out, and that I'm not going to show all those little steps. But if it's almost like a multiplying out a polynomial of two binomials. Multiply that out, and you'll get A dot A plus 2A dot B, and they're not like, it's a dot product, right? Plus B dot B. And then A dot A is magnitude A squared. And then plus 2A dot B. And then B dot B is magnitude B squared. Okay. So then, by the Cauchy-Schwarz inequality, we can replace this A dot B with something greater. With, where'd it go? So A dot B is less than or equal to that. So this whole thing is less than or equal to replacing it with magnitude A, magnitude B. So it's equal to magnitude A squared. So, not equal to. I just said less than. So it's less than or equal to magnitude A squared plus 2 times magnitude A, magnitude B, plus magnitude B squared. And that is by Cauchy-Schwarz. There's an H in there. Okay, because by Cauchy-Schwarz inequality. And then that right-hand side factors. That factors to, that's a perfect square trinomial. It was magnitude A plus magnitude B, quantity squared. And then we root both sides. Square root both sides. And therefore, if you have the square of both sides, you can square root both sides. You end up getting the triangle inequality. Magnitude A plus B is less than or equal to magnitude A plus magnitude B. And that's it. Important triangle inequality. You will see if you're going on in future stuff all the time. Well, not all the time. You know what I mean? You'll see it often. It comes up a bit. So in this, again, this applies concepts we just talked about. All the properties we were just using are implied in here, a number of places. And so it's a good one to look at. Again, I'm not going to ask you like just prove it, because you can just copy the darn thing, but maybe something slightly different, or argue something about it, talk about it. Okay? Next will be 12.4, the cross product. More good stuff.